Alright, welcome back. So in this video, we are going to look at stationarity and then limiting distribution. Or in other words, we call it stationary and limiting distribution. So when you hear stationary and limiting distribution, we would like to look at the long run behavior of the Markov chain. Okay? Yes, as in the example I've always been given, that is the MTN stock example, and that of Google. You have several stocks that your company can invest in. You have Google, you have Apple, you have S&P 500, and so forth. So you want to look at it this way. So in the long run, are we going to get an ideal investment strategy or stock that we are going to be investing in all the time? Is it going to be Google that even in 10 years time we will be great investors of that particular stock? That is what the limiting and the stationary distribution seek to address. Okay, the long run behavior of it. What is it going to be? You understand? Yeah. So as the end becomes larger, as the time progresses or elapses, so what is the way or the pattern in the behavior of the Markov chain? Okay. Yeah. So let's look at this example. So this Markov chain actually this is a transition diagram. So we want to look at the chain or we look at the limiting behavior of this. Okay. Yeah. So A and B are just normal, just two real numbers in the interval 0 to 1 because they should be what chosen in a sense that they should meet probability values. Okay. Yeah. Like that A plus B should be between 0 and 2, right? And not two inclusive, not one inclusive, zero inclusive two as well. Suppose that the system is in state 0 at time n is equal to 0, probability alpha. That is, we have our initial state to be what? To be alpha and then 1 minus alpha. Because if it is not in state 0, it will be in state 1 and they are complementary. Remember we said if you add this row, you should get 1, right? Great. That's okay. So for now, by using induction, we want to know, okay, want to know the this expression that you have seen here, okay? Yeah. So want to know this. So this is a formula you should know, alright? Yeah, great. So we want to show all these things in our proof. So if n is equal to 1, let's see what happens. So we're just going to get this expression. So this whole thing is what we are expressing over here. Nothing has actually changed. Okay. Yeah. So if you multiply everything by this, I think you should be very fine. We just try to break it down to make things very simple. Alright. Sure. Mhm. So everything here actually is like this. If you simplify it, you end up getting the same thing as here. Okay. Yeah. So by induction, so this is the first proof. So yeah. So as you do this, you're going to end up with this is just algebra. So you can just look through and try to simplify it for yourself. Okay. Yeah. Great. Great. Yeah. So we use convergence theorem. Yeah. Convergence theorem. Okay. Yeah. That's okay. So once we do, we can find the limiting behavior. So we end up with this. That's b over 1 a plus b. Then the other entry is a over a plus b. So that this is what we call the limiting vector. Okay, that's the limiting. It's sometimes called the limiting distribution. Okay, of the Markov chain. That's okay. So let's look at limiting probabilities. So those two entries you see are all limiting probabilities. Okay, and they are conditional probabilities. All right. Yeah. Limiting distribution. So usually we say that you have a limiting distribution. The Markov chain is called a limiting distribution. This pi you have seen. I want to say that this pi should be a limiting distribution. If when we multiply pi by the transition probability matrix, we should get pi back. So if that happens, then pi is said to be the limiting distribution for the Markov chain. And remember, this is a vector, alright. But once there are probability entries, when we sum the row, this row, entire row, we're going to get 1. Okay, Good. Yeah. So like I was saying, the aim of all these expressions is to arrive at this. So pi should equal to what? Pi p. It means when I multiply the vector by p, I'm going to get it back. You see, I'm getting pi back when I multiply pi by the transition probability matrix. So if that happens, then the limiting distribution pi satisfies the stationary condition. You get it? The limiting distribution is just what you have seen, that's the pi. But if you're able to multiply it with, it's like we're trying to get an image of it, but it gave us its own image. We multiply pi by p, and it gives us pi back. If that happens, then the limiting distribution pi satisfies the stationarity condition. Alright? Yeah, that is pi should equal to pi p. Okay? Yeah. So this is okay. That's very okay. Yeah, that's okay. So let's look at this example. So we are saying that is this chain irreducible? Is this particular chain irreducible? This all in one question. So let's stay tuned and see how and try to answer some questions for ourselves. Okay. So is this chain irreducible? We say that recall a Markov chain is said to be irreducible if all states in the word Markov chain communicate. So let's see if there's communication among these classes. Okay. Yeah. So as you can see clearly, this Markov chain is irreducible because we can go from any state to the other state in a finite number of steps. Okay. So is this chain aperiodic? So let's answer that question too. Is it aperiodic? Yeah, there's a self-translation. Remember, for aperiodicity, just look for a self-translationer, right? See, at 2, at state 3, and that was state 1, we have self-translation. Even there is just only one self-translation, then it means that the chain is aperiodic. So we've answered that one too. So find the stationary distribution for this chain, right? Stationary distribution. So over here, this is where we have to revise on how to do matrix multiplication. Okay. So here we have to take pi and multiply by p, and by doing so, you realize that we're going to end up with so this is 1 over 4. Okay, 1 over 4. Okay, I wish I could write this matrix down. I wish I could write it down. Just give me a second. Give me a second. Let me write it down. Yeah. So all you need to do from here, let me help you on how to get this. So you have to write the matrix down and try to do matrix multiplication. Multiply pi, which is equal to pi naught plus pi 1 plus pi 1 plus pi 2 and then pi 3. Try to get that this equation is done, and once you do that, you're going to get then also know that the condition that the pi should come to 1, then you solve this simultaneously to get your answers as pi 1 3 over 8, pi 2 3 over 16, and pi 3 7 over 15. So now our last question was that is the stationary distribution a limiting distribution for the chain, right? Let's answer that. So since the chain is irreducible and aperiodic, the stationary distribution is also the limiting distribution. So note, for the stationary to be the limiting distribution, then it means that the Markov chain should be irreducible and aperiodic. So once that is done, it means that we have satisfied our demand. Okay, yes. So thank you so much for your time being and your patience throughout this whole um, process on Markov chain. So this is the end to the video for Markov chain. God bless you. See you in the next semester or Stochastic 2 courses. Okay, thank you so much. God bless you.